Hello, and welcome to the presentation on risk assessment and optimal allocation of security measures under stealthy false data injection attacks. I'm Sri Balaji from Uppsala University, and this is a joint work between me, Andre Texeria, and Anders Allen, all from Uppsala University. The overline of this presentation is first, I try to motivate the problem and then describe the problem and then the system, the closed loop system that we consider. And then we formulate the problem. We have some preliminary results to solve the problem, and then we provide some conclusions. To begin with the motivations, there are several cyber attacks on networked control systems, which has happened over the past. A couple of examples include a denial of service attack on the Ukrainian power grid in 2015, and a data injection attack on the Kemuri water distribution company in 2016. And there are many more, like the Black Energy attack and Stuxnet, etc. So given that there are a variety of attacks which we have seen in the past, I think the main lesson here is to be proactive and protect the system. Protect the system in an optimal way. So that is what the main motivation of my presentation is. So the main problem that we consider in this talk is that given that we have an uncertain networked control system and that this system is under attack, how to design the system parameters such that the risk of the attack disruption is minimized? This is the main research question, and in particular, the question that we will be focusing on in this presentation is to, given that we have an uncertain network control system, how do we optimally allocate the security measures to minimize the system disruption? If there is a need for better understanding, let us consider a control system where there are two sensors, and we do not have perfect knowledge about this control system. There is some uncertainty. Now you have to decide if you can protect only one of the sensors, which one do you protect? By protect here, I mean some form of encryption, such that an attack cannot happen on that sensor channel. So this is an example which motivates our talk. There has been no work in the literature which focuses on this problem for uncertain systems, but there has been some works on deterministic systems, for example. So now, to formulate the problem more clearly, we describe the system. So we consider a process, a linear time invariant process, which has uncertainty over all the system matrices. And that is on one side of the network. On the other side of the network, there is the controller and the detector. Here, we consider parametric uncertainty, where there is a nominal matrix and an uncertainty matrix, which belongs to a closed bounded convex set, omega. Also, the actuator signal U tilde is the actuator signal generated by the controller plus some form of attack. Here, BA denotes which of the channels are under attack. Let's say we have two actuator channels. Then if BA is 1 and 0, the operator believes that the second actuator channel will not or cannot be under attack because it's encrypted. Whereas the first actuator channel is very prone to attacks. So when we solve the allocation problem of which of the actuator channels to protect, we we technically design this matrix BA so as to which of the sensors or which of the actuators to protect so that they become immune to attacks. So this is the system that we consider, and then some of the assumptions that we assume in this paper are that we assume that the adversary has perfect system knowledge, that is, he does not have uncertainty in his or her model, whereas the system operator is uncertain about the process. So this is a very unfair or unrealistic setup, but this setup can help us study the worst case. So we consider an adversary with complete system knowledge injecting false data into the network so that the performance cost increases, which is kind of intuitive if you imagine it, because if you consider an LQ controller, for example, it will always the motivation is to maintain the performance cost very low. Here, the adversary will just try to do the opposite, to increase, and while staying undetected. Here, by undetected, I mean that the energy of the residue signal is below some epsilon. So this is the system that we consider. Next, we come to the problem. So again, to recall, the main problem is that given that the operator is uncertain about the network control system, how to optimally deploy the security measures. This is the main question here. Okay. Now, to begin with, for any given uncertainty, delta from this set, we can characterize the disruption as this optimization problem, where the maximum disruption caused by an adversary is the maximum performance loss induced by the adversary while the adversary stays stealthy. So this is the maximum system disruption, or the impact I. This initial condition is for some technicality. So for the system operator, since this uncertainty is unknown, or the exact realization of the uncertainty is unknown, this the IM of delta becomes a random variable. So the best way that the operator can address this is to use some form of risk metric to address the uncertainty. So there are different measures of risk in the literature. One of them is value at risk. So if this is the probability density function, where the y-axis is the frequency and the x-axis is the loss, and y-axis is the frequency at which a certain loss occurs. Value at risk, if the value at risk is 1 minus alpha, it means that the weight of the tail is 1 minus alpha, that the mass of the tail is 1 minus alpha. And the conditional value at risk is the mean of the tail, and the maximum loss is the maximum value of the loss across the tail. So these are the different risk measures in the literature. And these risk measures are used to generally address some form of uncertainty. So in the current literature, we adopt value at risk. And value at risk of this impact, which is the uncertainty, is a measure of the attack impact without uncertainty. So the impact variable, the IM delta, is a random variable of delta, and then we use this risk metric to take away the uncertainty. So this is the overall picture. So the first step is to find the value at risk for the given IM of delta. So for the given random variable, the value at risk this is just simply the definition of value at risk of this random variable. However, computing this value at risk is difficult since the set omega is continuous. There is a probability operator operating over the set omega, which is continuous. So once we obtain this approximate value at risk, the allocation problem becomes something similar to this. Here, if you recall, as I mentioned before, BA and DA, here we focus on actuator attacks, but a similar thing can be done for sensor attacks. BA is the matrix which encodes which of the sensors, which of the actuators are under attack or not under attack. So this is essentially the matrix that we design in this optimization problem. So the main message here is that once we obtain an approximate value of this value at risk, we can go and try to solve this allocation problem. So the contributions of this paper is that firstly, we use the scenario approach to compute the approximate value of the value at risk. And then we propose an algorithm to solve the allocation problem. Next, I discuss some of the results. The first result is that we propose a way to compute the approximate value at risk. I see there is a lot of math here, but the main message is that the value at risk can be obtained with an accuracy and a confidence by solving this optimization problem, where the p hat is an approximate probability operator, which operates over a sampled set from omega instead of the continuous set. So by accuracy and confidence, I mean that the difference between these two probability operators does not exceed epsilon1 with a probability less than beta 1. So this is a convex semi-definite problem, so we can solve it in easily. The proof of this theorem is in the paper, and I invite you to read it if you're interested. Secondly, we provide an algorithm to solve this optimal allocation problem. So here, what we essentially do is that we determine the set of all vulnerable actuators with maximum cardinality NW. Here, NW is the number of secure resources that we have. And then we try to solve the risk, we try to measure the risk, and then we protect the elements which yield the least risk. This is the algorithm in an outline. Next, we consider this example. This is again a linear time invariant system where the system has one uncertainty here. Here, these are the results. Here, the text on top of the bar denotes which of the sensors are protected. So if, and the blue denotes the value at risk. So after protecting sensor 3, the value at risk is around 100. After protecting sensor 1, the value at risk is around 250, and so on and so on. So as you can see, if there is only one measure, which is one security measure, which is available, you have to protect sensor 3. So this is the conclusion that we draw from here. And in red, we denote the impact of the nominal system without using the risk metrics at all. Okay, it's just the nominal system. And if you use the same logic to make a conclusion of which sensors to protect, you end up protecting sensor 2. So the main message that you have to take away is that without using all these risk measures, you cannot derive the same conclusions as using the nominal system. So there is a difference here. And the conclusions are that we considered a system with uncertainties. We proposed an algorithm to solve the optimal allocation problem, and we demonstrated the results through numerical example. Thank you, and I invite you to ask questions.